So in this adventure in algebra, we're going to study the third isomorphism theorem. So the third isomorphism theorem states, suppose you have two normal subgroups of G with N a subset of H. Then, well, they write it one way, but I usually prefer to write it another way. If you take G mod N and you mod out by H mod N, so a double quotient, so to speak, the resulting group is isomorphic to G mod H. So in some sense, you can cancel out these denominators. So theoretically, if you write these this way, it looks like you're just multiplying the top and bottom by n and canceling. Worth pointing out, the reason why we always do this slash is to remind ourselves that we're working with left cosets, because the G is on the left and the subgroup is on the right. That's the reason why we do the slash instead of this vertical notation, although the vertical fraction notation is technically correct as well. But here's the point. This is morally true. Well, it's not equality, it's isomorphism. The proof is to use the first isomorphism theorem. So rather than construct an isomorphism, I don't know how you would do that. I guess you would need to define a homomorphism from here to here, which would be a bit of a pain, and show it's surjective and injective. No matter which way you decide to define a function, you have to define it on a set of cosets. So chances are there's some sort of well-definedness problem. So it's a bit of a pain. So instead, the tack we're going to try is to find a homomorphism from G mod N to G mod H and show that its kernel is H mod N and show that its image is G mod H. And so what would be a good choice? Well, a typical element in the domain looks like a coset G capital N. What would be a typical coset in the codomain? Well, G capital H. Good news, since N is a subset of H, it is certainly the case that G sub N is a subset of G sub H. That's a fact we will probably need in this proof. So there's our function. There's still a problem with well-definedness we need to show, because this formula we have is using this little letter G, which means that we're using a specific coset representative. So we still have to show that if Gn were equal to G prime N, then we still get phi Gn is equal to phi G prime of N. In other words, that GH is equal to G prime H. Well, that's not too hard to show, because since Gn is equal to G prime N, that's if and only if G inverse G prime is an element of N. By our hypothesis up here, N is a subset of H. So G inverse G prime is an element of H. That's true if and only if these two cosets of h are equal. So that's all we need. Now we need to show phi is surjective. Well, how do we show that? Well, take any coset on the right. And we need to find a coset that maps to it. Well, then phi of gn will work. So congratulations, phi is surjective. The remaining step we need to check is that the kernel of phi is what we claim it is. Claim that the kernel of phi is equal to h mod n. So how do we check this? Well, what does it mean? So we're looking at cosets. Gn is in the kernel of phi if and only if Gn, hold on. So Gn is a coset, and phi of Gn, which is Gh, is equal to h. Well, that's if and only if you're looking at a coset Gn. And what does it mean for Gh to be equal to h? Well, that only happens when G is an element of h. So we're looking at cosets of n where the representative is an element of h. So that means that you're actually looking at a coset of h mod n. Therefore, the kernel is h mod n. So finally, we have to recap, we have, well, I still need to show it's a homomorphism too. So given two cosets, phi gn, phi g prime n, the product of the images is gh times g prime h, which by definition is gg prime h, which is exactly what you get when you take the image of gg prime n, which is exactly what you get from the product. So congratulations, it's a homomorphism. So the first isomorphism theorem tells us that our domain, which is g mod n, modulo the kernel, which is h mod n, is isomorphic to the image, which, because we're surjective, is the whole codomain, which is g mod h. So there's the proof of the third isomorphism theorem. All right, let's look at an application. Suppose I let G be Z mod 24Z. 24. And I let H be the cyclic subgroup generated by 4. And I want to ask myself, what does G mod H look like? Well, one way would be to actually try to figure out the isomorphisms, but another approach using this isomorphism theorem we just saw is to realize that H itself here, these are multiples of 4, mod 24. Right, because what is this? It's 0, 4, 8, 12, 16, and 20, because 24 is 0 mod 24. So my point is, what is this G mod H? It's really Z mod 24Z modulo h, which is 4z mod 24z. By the third isomorphism theorem, you now see that you've got the cyclic group C mod 4z. So now we've actually figured out which group we're working with without actually doing the calculations. And so this gives you a way to check your work, because what would you have gotten for cosets? You would have seen that you could have gotten 4, 1 plus 4, 2 plus 4, and 3 plus angle brackets 4. And then when you wrote down the multiplication table, you would have seen that you actually had z mod 4z. But by using the third isomorphism theorem, you're allowed to shortcut that work.